camera gonna go? Okay, so we're talking about, this is another day on 6.2. This idea is important enough that I want to show you again kind of what the deal was. So we were talking about the change of variables theorem, but the most important part of the change of variables theorem for what we're going to do going forward is related to this idea. Ultimately, what we want to do is we want to look at integrals of surfaces. And the way to think about where we're going with this is a surface, in the way that we've looked at it before, is something like z is equal to f of x and y. I give you a domain x and y, and the z is the height that sits over that point x and y, right? That's what a surface is. What we're going to do instead is we're going to view a surface as a map that takes in little rectangles in some plane. So if I have a little rectangle here in R2, and instead of spitting it out into R2, I push it up into R3, I could map that little rectangle into space by distorting it into R3. So this is called parametrizing a surface. So I'm going to view the surface not as a function of x and y, but as a map that takes a domain in R2 and pushes it into R3 instead. So this map T, we're going to study this with exactly the same tools that we're doing with the change of variables theorem. So this is sort of in our future, this is where we're going. If you want to read ahead, this is not something you would have seen in any detail in 241 probably. So this is called parameterization of surfaces. It's the most important part of dealing with surfaces is that you can view them as maps from R2 to R3. If you've done anything with manifolds in the past or know what the word manifold means, the fact that I can do this is what it means to say a surface is a two-dimensional manifold. If you have no idea what that means, don't worry about it. Okay, mostly what I want you to think, like all the word manifold means in this context is, I think of this as two-dimensional because it comes from a two-dimensional shape. A curve is one-dimensional because a curve is the image of an interval. A surface is two-dimensional because it's the image of a rectangle. So, with that in mind, the important part of this is that we talked about last time is I want to talk about this particular example. So I'm going to start with a set in the r and theta plane. And that set is going to look like the following. I'm going to put a point right here at 2 comma pi over 4. And in the r direction, I'm going to allow myself to go from 2 to 3. So I'm going to make a little rectangle. So this is 3 comma pi over 4. And if I go this direction, I'm going to put this corner at 2 comma pi over 3. And so this corner will be at 3 comma pi over 3. So you'll agree with me that's a little tiny rectangle in the r theta plane. So what I want to do is I want to take the map T and I'm going to transform this with a polar coordinate transformation. That is, I'm going to let x be equal to r cosine theta and y be equal to r times the sine of theta. And when you do that, let's see, 1, 2, 3, pi over 4, pi over 3. I think that the shape we get out here is this region right here, where we go from radius 2 to radius 3 and pi over 4 to pi over 3 in angle. So this is the image of the rectangle that we started with. So I'm also trying to emphasize the language that we're using. So this set up here is what we call the set D star. And this set is T of D star, the image of the original rectangle under the transformation. So what I want to do is I want to study how I can recover an approximation for the area of this if I only knew if I knew this area and I know the map. Can I calculate this area without actually calculating it? Can I calculate this area without having to do geometry to figure it out? Can I just start with that area and multiply it by some number to figure out what this should be? So the way I'm going to do it is I'm going to think about this rectangle as being comprised of a vector that points this direction. So the corner down here is the corner 2 comma pi over 4. That corner got mapped right here. That's the image of 2 comma pi over 4. It started here, it ended up right there. This edge of the rectangle and this edge, I'm going to think about those as vectors, and I'm going to figure out where the vectors moved under the transformation. This is what the image of the rectangle is, but where do the vectors go? So the claim was, so if I think about a blue edge right here as one vector and a purple edge as this vector, the claim was that the derivative of the map, the linear approximation, treats this thing like a parallelogram that it's transforming from this parallelogram into a parallelogram that sits in that picture. So let's just see what it is. This is what the function did. What does the linear approximation do? So we defined two vectors. We defined, we looked at the map dt, which is the derivative of t, which was dx, dr, dx, d theta, dy, dr, dy, d theta. And if I wrote that matrix down, I'm going to get cosine theta minus the sine of theta, no, that's not right, minus r sine theta, sine theta, r cosine theta. I think that's the derivative of the transform. And then we made the definition that this column of this matrix is called TR because it's the r derivatives of the two functions. This column was called T theta because it was the theta derivatives of the transformation. And the claim was that TR and T theta build us a useful rectangle in the image. So specifically, the rectangle I'm going to build looks like this. I want to calculate TR delta U, delta, not U here in this case, delta R, and T theta delta theta. Those are vectors. I want to calculate them and then draw them in the picture over there to see what they look like. So delta R is pretty easy. How far did I go in this direction? 1, right? 1 unit, from 2 to 3. So delta R is 1. What is TR at the point 2 pi over 4? They're located at that vector. So the vectors are anchored at this position. So I'm doing a linear approximation at that position. The derivative in that position is, okay, cosine of pi over 4, sine of pi over 4, which is root 2 over 2, root 2 over 2. So if I want to calculate this, TR delta R, I should take the vector root 2 over 2, root 2 over 2, because that's TR, and multiply it by delta R, which was 1. This is the vector TR delta R. And if I take it, and I plot that vector over here, it says it's a unit vector pointing at a 45-degree angle of length 1. So here it is right here. In fact, falling exactly on the side of that original region that we drew. This blue vector right here is the vector TR delta R. Okay, let's look at the other one. Let's look at T theta at the point 2 pi over 4. Well, a quick calculation will show you that this is equal to minus root 2, root 2. That's a vector of length 2. Basically pointing in the minus 1, 1 direction. So T theta, delta theta, is going to be the vector minus root 2 to root 2 times delta theta, which is from pi over 4 to pi over 3, pi over 12. So all I've got to do is think about a vector pointing in this direction. So minus 1, 1. So in this direction of length pi over 12, I'm going to cheat and just draw something here instead of actually trying to draw this accurately. So you're supposed to believe that that vector right there is T theta delta theta. That's the vector pointing in the direction I want, and it's scaled by the pi over 12 to get it to be the right length. And the claim is, this is the claim of this whole technique, using these derivatives to produce these vectors, this local framework, gives me a parallelogram that has about the same area that the yellow region did. And I can demonstrate that. So let's actually just do it. If I look at that particular parallelogram I just drew, so on this side I had t theta delta theta, and on this side I have tr delta r, and I finish it up into it's actually a rectangle in this case. Isn't the length of this side just 1? I mean, the length of that vector is 1. That's a unit vector, and if I multiply a unit vector by 1, I still have a length 1 vector. So I think this side has length 1. And the length of this side is, okay, so that's a vector of length 2, and I've multiplied it by pi over 12, so its length should be pi over 6. So I believe the area of this is pi over 6. This is a right angle here because of this particular frame that I've got a right angle. So I'm looking at a rectangle, so I can multiply base times height. I get pi over 6, which I'm going to write as 4 pi over 24 for reasons that will become apparent very quickly. So what did I do? I used the derivative of the transformation. So here's the transformation. I took the derivative, and I used it to produce vectors that make a parallelogram. And the claim is the area of that parallelogram is pretty much the area of the yellow shape. Well, let's see what the area of the yellow shape is. That's actually not so bad either, because what the yellow shape looks like is this. Something like this. That's radius 2. That's radius 3. The angle inside here is pi over 12. That's the arc. And so to calculate the area, I'm going to just take the big sector and subtract it from the small sector. So the area of the big sector is 1/2 of theta times the radius squared. That's the area of the big sector from the corner out to the outer circle. And if I subtract that from 1/2 times pi over 12 times 2 squared, the formula I'm using here is the area of a circle in radians is 1/2 theta r squared. It's standard area for the sector of a sector. And what does that get me? 9 pi over 24 minus 4 pi over 24, which is 5 pi over 24. So the actual area of the yellow region is 5 pi over 24, and this approximation that we cooked up for it is 4 pi over 24, which is pretty close. And you can see that it's not exact in the picture. If you completed this, you can see, okay, well, it's not quite exact. There's pieces sticking out that we're not catching because it arcs outside the rectangle, but it's pretty close. And if we made these rectangles smaller, this approximation would get better. So essentially what this is demonstrating is that the area of that region, so dx dy, is about equal to, so I guess really what we've demonstrated here is that the area of t of d star the area of that initial region is approximated by the parallelogram, or the area of the parallelogram given by tr delta r and t theta delta theta. That's what the demonstration was, right? The area of this parallelogram is about equal to the area of this one. And then all that the Jacobian identity was just a way of computing that area. dxy dr theta is just equal to this area. So that formula that we wrote down last time is literally just the way you compute the area without having to do it the way I did it. I want to be able to do this in general and not each time I write a rectangle down, figure out, oh, it's a parallelogram, I better multiply their diagonals or whatever the hell your favorite parallelogram area formula is. This is a fast way of doing it. So this is just a computational formula that is really just producing the magnitude of the cross product of these two vectors. So that's all it is. This geometric argument is the important part. The fact that these vectors exist and they form a parallelogram is the important part. Okay. So hopefully that's more concrete than the abstract way I did it yesterday. Like the TU, that sort of TU-TV, these are literally just a way of taking rectangle here and transporting it not to a non-rectangular shape, but to a rectangular one. Okay, questions about this? So, why does this have anything to do with surfaces would be a good question. And the idea is, in the same way that I think, so like, why do this? So one of the things that we're doing when we approximate the length of a curve is we break it up into straight line segments. We have, oh, look, I can approximate it with a bunch of straight line segments and then use the distance formula to approximate the length of the curve, right? A bunch of straight line segments. So I've straightened the curve out in some sense. If instead I wanted to do surface area, which you've probably never seen treated correctly, maybe you were given a formula, one way of calculating the surface area of a surface would be to say, well, what are some convenient things to break it into? How about little parallelograms? Right? I mean, the parallelograms are not going to exactly sit inside the surface because the surface could be curved, so the parallelograms are sticking off the surface. It's just to sort of think like armadillo skin or something here, right? Like you've got a curved surface that you're approximating with flat scales. The area of the scales is pretty close to the area of the curved skin sitting underneath it, right? And so what we're going to be doing is using this kind of argument with these vectors that produce the parallelograms to take a surface and basically tile it with parallelograms. So if you've ever seen the surface area formula in your 241 classes that had the norm of the cross product of two vectors inside of it, it's literally what you were doing is producing the area of these parallelograms. You're just tiling it with scales. So we are going to get to a formal development of that, but that is why I think it's really important to keep in mind that that's what these vectors are actually doing. The derivative is producing the tiling. Okay, so let's take a look at a more concrete question now, which is, how do you actually do this? So let's take some examples from the textbook. So we can look, for example, at, let's see, the change variables formula. Okay, so here's one. Okay, well, maybe you haven't seen one of these in a while, so I'll write it down. So a really basic version of this is something like the integral of d over the log of x squared plus y squared dx dy. So we'll start with an easy example and move into something more complicated, where d looks like this. It's the area in the first quadrant lying between two different circles. So d is the region that looks like this. This circle is given by x squared plus y squared is a squared. This circle is given by x squared plus y squared is equal to b squared. And we're trying to find the integral of that function over that region. So by the logic of textbooks, since we're in the chapter on change of variables, it might be wise to try to use a change of variables to solve this problem. And in particular, if you haven't done this in a while, the change of variables that it really wants you to use here is a polar change of variables, because we're talking about a domain that is bounded by circles. So this is a polar rectangle. And even more sort of bait for you is the fact that there's an x squared plus y squared in the problem, right? And if you remember from your polar coordinate days, you get the transformation in one way looks like this. And the transformation in the other direction says r squared is x squared plus y squared. And then if you see a y over x, you can replace that with a tangent of theta up to making sure the domain of your tangent is set up correctly. Right? So this kind of gives you the back and forth that you use. So if we're going to change variables here, And we want to do this in the full way instead of the I already know the answer way. A squared. This is the way the textbook treats you like upper division students, I guess, is they don't give you numbers, they give you letters. Okay, so how do I set this up as a polar region? Like, what is the region that I could use to produce that? This is the way to think about this. What is the rectangle in the R and theta space that produces this particular shape? So this is easy if you just follow your nose, but I want you to think about what is the actual rectangle over here that maps to that change of variables. R goes from where to where? A to B. Okay. So from A to B. Theta between? Oh, I guess I should have written that over here. There's A, there's B, and 0 to pi over 2. Now, obviously, those of you that are more technically minded might think like, but look, we already know this is not a one-to-one map at the origin, but notice the origin has nothing to do with this. The pole where there could possibly be problems is not part of the question. So what we are doing when we do our change of variables is we are shifting the problem, so we're integrating over this rectangle instead. That's literally, it's not just like we're switching numbers out for numbers. We're actually changing the function so that instead of the function, it's like we're imposing a composition so that the composition untwists this shape into a rectangle. So what's the result? That integral is equal to what? There should be a natural log of probably r squared. We know that, so okay, if we were being extra precise here, we would write the absolute value of the derivative of x and y over the derivative of r and theta, dr d theta. And then I have to put like d star right here. But you know d star, right? You know d star is over a rectangle. So Fabini's theorem says that you should be able to do a to b and 0 to pi over 2. You've untwisted the problem into a rectangle. Yep.
Where did natural log come from?
Oh, okay, sorry. In like, I guess Marsden and Tromba always use log, but they mean natural log. And so my calculus brain like turned log into, there's only one log in the world, log base 10. Nobody studies earthquakes or sound. There's no intensity of light. There's just natural logs. Yeah, so I'm sorry. They write log in the book, but they mean log base E when they do it. Okay, so if you were being fully pedantic, you would then go over here and compute this Jacobian determinant. It's perhaps unsurprising that it's equal to r, since we've already done that. And you would get the integral from 0 to pi over 2 of the integral from a to b of the log of r squared times r dr d theta. And of course, that's going to be a u substitution. I hope everybody remembers how to integrate the log. How many of you off the top of your heads right now can tell me how to integrate the natural log? Not what it actually is, not how to do it, but what it actually is. Hit me.
I think it's like u log, if we switched it to u, it'd be like u log u plus,
Isn't it like u log u plus u?
Okay.
Isn't it minus?
Minus u. U log u minus u plus c. Right? You don't need to know that. You can do this by parts if you really want to. But, so yeah. So it's likely that if I give you these problems on a homework assignment, you can just, okay, I know probably what people do is they go take a picture of it and then Wolfram Alpha tells you what the answer is. But you should really remember how to integrate the natural log, right? Like, it's just one of the basic integration by parts. I will say that because we're going to go super integral heavy in this part of the class, on exams, these almost always are just set up the integral problems and I'll actually do them. So, I heard that. I like to grade these as little as anybody likes to do them. So, yeah. So you should, the important part of these problems, and I was just telling this to the 241 class, the important part is the setup of the problem, right? Figuring out what the change of variables and producing something that you could integrate that way. Doing the actual transformation is more important than calculating the integral when you're finished. So you should practice the technique on the homework, but it's unlikely, especially on a short test, that I can give you 6 problems that all require you to do basic integrals. If you've integrated a polynomial once, you can do it forever. Right? In fact, after I was grading your exam, I thought of a revision that I should have done to the second derivative problem, which is I should have just told you what all the second derivatives were. So, so maybe in the future, like on a final, I'll put an extra question on the test. That'll be the trade-off. I'll give you a shorter version of the second derivative test, but I'll just tell you the derivative. All right, let's do a more interesting question. Yeah, so for our purposes, that is the answer right there. Who cares, right? You could a computer can integrate that if it wants to. You guys have already seen the Gaussian integral. Come on, we got to get like a good. All right, here's a good one. How about this one? It's a good one in the exercises here. Let's look at. Let's do this transformation. Let's look at the change of, let's look at the double integral over d of, what do I want to do here? How about, oh God, it's the wrong direction. Okay, this is a good one. All right, 2. So we'll do. I'm recording this too. That's great. Excuse my language. Right. Okay. Okay. Let's look at x plus y, and then let's put an e to the 2xy up here, and then we'll integrate that dx dy. And then let's suppose that we're integrating over, I don't really want this to work, and it's not going to. Okay, never mind. I should have just picked a homework problem. Okay, let's do this. T of u of v is equal to 4u, 2u plus 3v. There's a transformation. A nice linear transformation. And let's let d star be equal to the rectangle 0, 1 cross 1, 2. So that's the input rectangle. And the question asks the following. It wants you to find d is equal to t of d star, so the image of that rectangle underneath this linear transformation. And then let's evaluate the double integral over d of xy dx dy. Okay, so how am I gonna start this? I gotta do something. Maybe I should just draw that rectangle d star. Maybe that's a good first step. Okay, so let's figure out if I want to edit my cussing out of your the video I'm going to post later. 0, 1, and 1 to 2. So we're looking at this rectangle right here. This is our original region, d star. Now, one thing to notice about this particular t is that t of u and v in this case can be written as the matrix 4, 0, 2, 3 times the vector uv. It's of the form ax plus, right? This is a linear transformation. The linear combinations of u and v in both slots. I think isn't that right? Like 4u plus 0v in the first slot and 2u plus 3v in the second. So what happens, this is the easiest possible case. How do I figure out what happened to the rectangle? What's the easiest thing to do? Well, okay, what do you mean plug it in? Plug what in? Put the corners in, right? With linear transformations, you just track where the vertices go. That's all you have to do. So this corner right here, the corner at 0, 1, where did it land? You don't have to do a matrix multiplication if you want. You can just plug it in right here. So where does 0, 1 go? 0, 3? Okay. 1, 2, 3. Okay, so red corner went right here. How about yellow corner? 1, 1. Where did it go? 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. There's the yellow corner. Hopefully, oh man, I leave myself a ton of room, did I? How about green corner? 0, 2. Is it 0, 6? Is that right? Now, I'm guessing that the next dot is going to be right there, since I know this is a parallelogram. Blue corner, which is at 1, 2, it's 4, comma 8. 1, 2, 3, 4, 5, 6, 7, 8. And we get this parallelogram right here. That is T of D star. Now, if I really want to, right, which is D, I mean, this is the region, T of D star is what they mean by D. If I really wanted to, if I wanted to calculate that integral right there, I guess I could. It would suck because this is a type 1 or type 2 region, right? Because if I try to do it this direction, I have to break it up into 2 integrals because the left function and the right function aren't consistent. And if I wanted to go top to bottom, I have to break it up. I guess maybe we could go from 0 to 4, and in which case this would always be the top line and this is always the bottom. But maybe I can get away with integrating on its original domain, right? As an integral with respect to u and v, it wants me to calculate this integral over that region. But if I could figure out a way to figure out like x and y as functions of u and v, I think the change of variables theorem says this is supposed to be equal to the original integral I mean, I guess this, right? I mean, isn't this x is a function of u and v and y is a function of u and v? I want to put this back in terms of the original variables, which means I would like this to be thought of as a function of u and v, and not a function of x and y. So what should I put there? X is 4u, and y is 2u plus 3v. So I'm using substitution. I have substitutions I can use. But the trade-off is, in this spot, if I want to put a du dv right here, I have to put dx du, dx dv, dy du, dy dv. I shouldn't write that. I should just write the actual symbol. This is why we invented it. dxy over duv. The Jacobian determinant of the transformation. That's our distortion factor. So what is that in this case? D of t is equal to 4, 0, 2, 3. The literal matrix I wrote down right there. I think that's true. And the determinant of that then, dxy duv, I think is just equal to 12. Can I clarify something for you? Okay. Does that make sense? I guess maybe we should believe that, because if the area of the original rectangle here was 1, because it was 1 wide by 1 tall, the area of this is definitely bigger than 1. Right? So you get blown up as you come over from uv into xy. So yeah, if I was just doing a setup question, this would turn into the integral, say, from 1 to 2 of the integral from 0 to 1 of 4u times 2u plus 3v times 12 because that was the distortion factor, and then the 0 to 1 was in the u direction, and the 1 to 2 is in the v direction. What we've gained here by writing this integral down instead of that one is if I wanted to do this in the xy variables, I have to do it this way. Okay, so that function right there has slope. So we start at 0, 3, and we end at 4, 5. So it goes up 2 and over 4. So it's y is equal to 1/2 of x plus 3. And then this one is 1/2 of x plus 1, 2, 3, 4, 6. I think. And so we have to integrate. So if I wanted to do it this way, now I've got the integral from 0 to 4 of the integral from 1/2 of x plus 3 to 1/2 of x plus 6 of xy dx dy. It's a doable integral, but there's trade-offs, right? We've traded an integral on rectangles for an integral where I've got functions in the limits of integration. Oftentimes, one way is much easier than the other. Okay? Okay. So let's do another example here. Oh, this is the exact one I was looking for. Oh, okay. Okay, so I wrote this map out earlier. All right, so here's a classic map. I did this in an earlier lecture. T of u and v is equal to u squared minus v squared 2uv. If you went back to your notes, this was the one that took rectangles and turned them into strips sitting between parabolas. So when I talked about 6.1, I think this took this box right here and turned it into this weird shape, like stuck around the origin as a parabola. And if I put another box out here, it turned it into this like strip thing between two parabolas. So highly nonlinear change of variables this time. So we have this particular change of variables we're interested in. And let's let D star be the set. Of u and v with u squared plus v squared is less than or equal to 1, u is greater than or equal to 0, and v is greater than or equal to 0. Find d, which is t of d star, step 1, and then evaluate the double integral over d dx dy. What is this, by the way? The double integral over d of dx dy, what does that represent? There's no function in here, so this is an area. If I integrate over a region with no function, I'm just calculating the area. So this is the area of d. All right, so we got a little bit more work to do this time. It is not the case that we're going to feed in a certain region and have something nice come out the other side. So what the heck am I going to do here? So I have, in my initial set, my d star this time is a quarter circle, isn't it? U squared plus v squared is less than or equal to 1. Isn't that the closed quarter circle? Especially if I say u and v have to be positive. So I've taken this sort of semicircular region. Semicircular? That's my d star. Oh man, what does t do to that? Well, maybe we can figure out what it does to the edges. Right? That's a good thing. Maybe the outside of the region will still stay the outside. The border is going to stay the border. So we can just track what happens to the edges. So every point on this edge, I think, has the form u comma 0. And if you remember from last time, I think what ended up happening here is, doesn't that turn into, so t of u comma 0 is equal to u squared comma 0, where the u values travel between 0 and 1, because that's where the u's are allowed to be on this line segment. So I think this line segment right here turns into this line segment. this line segment, where all the points have the form 0v, t of 0v turns into minus v squared comma 0, where v goes from 0 to 1. So that's a line segment that starts at 0, 0 and goes left until it gets to minus 1, 0. Okay, so we did that part. Now that circular arc part. What is going to happen to that? I guess the idea is we're going to say on that arc right there, so maybe I'll give that its own color, purple. So now we're trying to keep track of what happens to that part of the boundary of the original region. If I do that, I'm saying that x squared plus y squared is actually equal to 1. That's the part of the arc where that's true. Or I guess u squared plus v squared, right? U squared plus v squared is equal to 1. And I suppose that means that v squared is equal to 1 minus u squared. Okay. So I hope this turns out to be nice. It would be really great if it did. So t on that chunk right there where v squared is equal to 1 minus u squared, I think we're calculating t of, I have to put a square root in there. V is equal to the square root of 1 minus u squared, right? That's like the v variable on that curve. So I guess we're calculating t of u comma the square root of 1 minus u squared. Yuck. So the x variable is u squared minus the square of that, which is 1 minus u squared. Isn't that v squared? 1 minus u squared. And the other variable, we get 2 times u times the square root of 1 minus u squared. I have no idea what that curve looks like. This is a parametric curve that has 2u squared minus 1 in the x component and 2u times the square root of 1 minus u squared in the y component, and where the, maybe we should be doing this in polar coordinates instead. Would that maybe be a better way to do it? I don't even know. That's awful. And the u variables are going from 0 to 1. At least we know that, right? This curve is traced out as u goes from 0 to 1 in the way that we're writing it down right now. So u is between 0 and 1. So does anybody have their Desmos open? We can write down a parametric equation that describes this thing. I was actually hoping this was going to be nice, but maybe we can figure out where it starts and ends. Okay, if we've done this correctly, if I put in 0, I should start at that point right there. Is that true? If I put in u is equal to 0, I get -1 and 0. Okay, sweet. At least we got that, right? So the curve starts at the right spot. When u is equal to 0 and I'm at that point right there, I'm right here. Okay, what happens when u is equal to 1? I damn well better land at that point right there. More profanity. Sorry about that. So when I put in u is equal to 1 on that circle, so I go over here and put in u equals 1, I get 2 minus 1, which is 1, and 1 minus 1 is 0, so that's 0. So, okay, sweet, I'm right here. So at least we know whatever is happening above, that's true. Oh, weird. So it's some kind of weird looking, like thing like this. So the way to think about what's going on here is it acts like a square in the first variable and like kind of like a square in the second variable because you got a square root of a square happening. So it definitely has the feel of a parabola. It's probably actually 2 halves of a parabola in the other variable that are coming together here. So it's something like that. Now I don't know about you, but if somebody came along and said, so if you plot this thing as u runs from 0 to 1 parametrically, this is what you get. Somebody says calculate the area of this region here. I'm sorry, I've got no idea. I can't even write that thing down as a function of one variable. I got this parametric description of the curve, right? We don't have a shot. I have no idea what the area of D is. I'm pretty sure I know the area of that thing, though. Quarter circle. So maybe, if the problem really wants us to calculate the area of D, we should use the change of variables theorem so that we're calculating something as a multiple of the area of D star instead. So that's actually the trick we're using here. The problem says, okay, now take all that crap you did and find the double integral over D of dx dy. That is, calculate the area of that region. But I don't want to. So instead, I'm going to calculate the area of D star. Notice there's not even a function to substitute like x's and y's into. So all I have to do is figure out this. And integrate that instead. Okay, so let's do it. dx y d uv is equal to 2u minus 2v 2u. Matrix of derivatives. The determinant of that. What's the determinant of this? That symbol means determinant, not the Jacobian matrix. So the determinant of this, which is 4u squared plus 4v squared. That's always positive, so we can throw the absolute values away. And now notice, this problem has now basically boiled down to, after all this work and figuring out what happened to this region, the problem now boils down to the double integral of dx dy over d is equal to the double integral over d star, which is this semicircular region of 4u squared plus 4v squared du dv. And that looks an awful lot like something you could do with a polar substitution. Because now, instead of integrating this god-awful mess, where you can't even write down a function for what this region is bounded by, you can pull it back and integrate over this quarter circle, and the function has a u squared plus v squared in it, so you could use polar coordinates if you wanted to. So this is typical of the way the change of variables theorem gets used, right? Regions that are complex on one side of the transformation are nice on the other side, and as long as the change of variables Jacobian thing is not too complicated, the integral turns out to be doable. Okay. So you should practice these and put a focus not on calculating if you have limited time. I mean, this really should be the most important class in your life because I'm teaching it. Obviously, this is all you should be doing. And forget 413 or whatever high-level physics or engineering class you're taking. No, you should be doing integrals. But if you have limited time, you should put your focus on doing the setup for these integrals and not spending the 30 or 40 minutes grinding these out to single numbers when you're finished. And I will tell the grader to look for setup integrals and not final answers. The focus here should be on doing this step. All right. See you guys on Thursday. Yep.